Okay, okay. I agree.
Okay, Massimo.
Yeah, I think that there is no one joining, so we can start. Okay, so welcome everyone to this new question and answer. So I hope you came prepared with some questions like the last time. So if anyone has questions, you have some doubts, something you want to discuss about, please go ahead. If you want, Valentina, you can start with if you have some questions related to the section cut.
Actually, if everybody maybe puts also the camera, it would be nice if someone wants to. What do you think, Massimo?
Yeah.
Last time
if you want to switch on your cameras, your microphones.
Last time we all were with cameras and it was very, very nice. It was like you feel the presence of people. Okay, I think I can start while we are waiting for other questions. In my case, I just wanted to discuss with you this negative sign or positive sign. I can share the screen because it's still, I know that it should be simple, but it's still not clear for me how we should do it.
Yeah, so probably what you can do is to, if you have your model, if you want to introduce a little bit of what we have done to other people, because they don't know about this tool of section cut. So you can explain what it does. And then we are going into the details.
Okay, okay. I will share my screen.
Can you share it or should I give you permission for sharing it? I think you can share it. Okay.
Okay, I think yes. Can you see it?
Yeah.
Okay, just to introduce my work, I'm working with frame infill interaction. So I have masonry and I have reinforced concrete frame. I simulated between them to be able to have friction and also detachment, so it's more refined model. And everything is in 2D continuum model. So the problem was how to measure shear in frame in column where we have additional shear due to infill. It's my point of interest, field of interest. And as I'm working with 2D continuum model in comparison with 1D when we use fiber section, it's much more complicated here to measure shear. And what Massimo offered me and helped me, it was a script that we are using here that allows us to measure shear. In my case, I'm measuring shear in 6 different sections where I expect the maximum. So it's a left upper angle of column. You can see it's in red, and also 3 section cut here. I can explain a little bit how we did it, just for someone who is also interested in this.
Yeah, just to explain to everyone, probably I can do a drawing just to explain what's the problem. So typically, when you model this column as a beam column element, okay, so imagine this concrete column is modeled as a beam column element, okay? Now, when you do this, you already can visualize the beam forces like normal force, shear, bending moments. So it's very easy. If you want to look at this Gauss point of the beam, you can get the entire shear at this point. But she needed to model it with continuum elements for a series of reasons, okay? Because she needed to take into account stirrups, the contact between infill and concrete. So for some reason, she needed to model the concrete frame with continuum elements. So instead of having a column element, she has a set of 2-dimensional elements, okay, with all discretization in finite element meshes. Now, when you have continuum elements, either 2D or 3D, you cannot measure directly the entire shear that you have at a certain point. What you can visualize is the shear stress, okay, or any other stress in the other direction, but you don't have the total shear like this. You can visualize it, for example, if you have a fixity at the bottom. Here you can visualize the total base shear because it is the opposite of the sum of the reaction forces. But if you want to measure the shear in between your model, you cannot do that. So what we did is to create a script where the user basically can specify a set of nodes inside a 2D or 3D model. And this script is able to take the internal forces of the elements, and taking these internal forces, it will integrate them along this section in 2D or along a face in 3D, okay? Then you will see in the details of the script, you also have to specify a reference coordinate system, okay, which coincides with the axis of the beam, like the axial direction of the beam and the two transverse direction. So all the stresses that we have along this section cut can be integrated to compute the total normal force, the total shear forces, and the bending moments about the different axes, okay? So this is a brief summary of, so it's very easy to explain actually, but the implementation is not so easy. There are a lot of aspects, and probably, Valentina, you're still confused about some aspects, so we can clarify them. Just another point, this feature was not available in STKO, so I did it using a TCO script, okay? But since we think it is very necessary to a lot of people, in the next version of STKO, this one will be a built-in feature in STKO, okay? So you will be able to select a set of continuum models, decide where you want the section cuts, and the post-processor in STKO will perform the section integration directly, okay? But for the moment, we need to use TCO scripts. Okay, so go ahead, Valentina.
Okay, I will just explain what we did by procedure, because if I don't know anyone needs it now, that it can help. So you need to choose your section cut where you're interested in shear. In my case, it's here. I also wanted to discuss that, for example, as in my case, I use contact here. It should coincide with the mesh. Otherwise, we should draw a new line, because in our case, because of contact between masonry and concrete, if cut will be, I don't know, between the mesh, it will not work. So it should coincide with the mesh, or we should, I don't know, to draw additional line also in infill.
Exactly, now your section cut should coincide with the mesh. But in the feature that we will implement in STKO, you will be able to draw a section cut even passing through the elements, okay? Because there is a way to do some kind of interpolation. The problem is that it was difficult to do with TCO. But I will be able to do it inside STKO once.
Okay, okay.
This is a limitation for the TCO version.
I wanted to mention just because for implementation. Okay, so we need to create selection sets. In our case, it's 6 cuts, because then later in analysis, we will create regions, as we discussed also last time about regions. And in regions, we need to choose this selection set that we chose before. We are working with nodes. We also named every cut. So we have a name, and we have here we chose our selection set. After we created 6 regions in this case, the main thing is begin section cut, where we use our TCO script. So it's custom command, and here we have our TCO script. And here I have some question. Okay. Okay. My question is about cut sides. That this is first one should be negative.
Yeah. Why the first one should be negative?
I will come back here.
Because for example, select the selection cut number 1. You will see. Then I will explain you why you need to put -1. Okay, is the one up there, okay?
This is, yes, the first one. And as I see, my X direction coincide with global.
Not in your, okay, these directions here are the direction of the shell, okay? But if you go inside the script, okay, you go inside the script, the local direction that I've chosen is the one that you typically give to a beam. Okay, so the X local axis is the axial direction of the beam. If you look, okay, keep it like this. Let me do some annotation. So first of all, here you have to list all the names of the cuts that you want to process. Okay, so you have six cuts, and you put all of them here. Okay. Then, so this one basically is a list with the cuts names. Then I create another list with the same number of components. So you have 6 cuts, and also here you have 6 entities. Now you are in 2 dimension. Every entity, so this one is an entity for the first selection set, and so on. Okay. Every entity is the orientation vectors. Okay. Now you are in 2D, so I only need the first axis, which is the y-axis, and the second axis, which is written here. The x, which is the first one, is the beam axis direction. Now, in your case, your column is pointing toward the global y direction, okay? Because you are in 2D, okay? So this one is your beam. Actually, this one is your wall. Now we are looking into this beam. So the axis of the beam is this one. This one is the x. Okay, the global axis are this one, x and y, because you are in 2 dimensions. Okay, the axial direction of the beam coincides with the global y, and in fact it is 0, 1. Okay, which is this vector here, which is parallel to this one. What is the other axis? For the other axis, you need to take into account that the third axis is always global z. Okay. Since it is global z, for the other direction, which is the dz of the beam, you need to take the cross product of z and y. So if you do the cross product of z and y, the outward normal vector is this one, which coincides with -x. That's why I have it here. Okay. So remember that in 2 dimensions, you cannot choose the global z direction. It's always pointing outward from the screen, okay, which is this one. So if you do the cross product between z and the axis of the beam, the x, you obtain the y, the z of beam, which in this case is equal to -x, right? Otherwise, you will have some problems because you will see opposite signs of these section forces if you put the x on the other direction, okay? When you are in 3D, instead, you can choose the x should always be the axis of the beam, and dz and dy are the 2 directions of the cross sections, okay? But in 2 dimension, the dy of the beam is always pointing in the same direction of the z global axis, and the dz comes from the cross product, okay? Okay, now let me clean this one. For simplicity, I said that I want the same local axis for all the beams, okay? So I have my beams here and the other column here. Now, section cut 1 is up here, right? While the section cut 2 is here, section cut 3 is here, and then we go to 3, 4, and 5, which is, I think, oh, let me draw it here. 6, 4, and 5, 5 and 4. Or I don't remember what is 6 or 4, but it's the same. Now, if you draw the x local axis for each one of them, you will see that it is this one, and this one, and also here. Okay. Now, the point is that the algorithm works by looking at the elements near the cut, okay? But when you have a cut in the middle, like here, okay? Let's do a zoom here. You have finite elements on both sides, okay? So this one is my selection, this one is my cut. Here, there is my dx direction. So I take the elements which are in the same side of the dx, okay? So basically, I need to choose some elements from either one or the other side of the section cut, okay? Now, by default, I choose the same one, the ones that are in the same direction of the axial vector. Okay, so basically these ones. Doing so, I can take the internal forces with the same sign, okay, with the positive sign that they have. But sometimes it may happen that the section cut is at the end, okay, and in this case, I cannot get elements from here. I only have elements from the opposite direction of the dx vector. In this case, I need to use a multiplier which is -1. That's why I used -1 here. Okay, because I need to choose the element from the opposite direction of the section cut. And since my forces are on the opposite direction of the section cut, I need to change the sign. It's just a sign convention. Okay, so keep in mind basically that you first decide where the selection cuts are. Then you decide the orientation vectors. Finally, you need to choose the sign, the multiplier, based on this side. Now, if you have elements on the direction of the axial vector, you can keep a sign equal to 1. If you only have elements on the other direction, you put -1. Is it clear?
Yes, yes, Massimo. Thank you very much. Yeah, now it's clear.
So this one is the only reason why we need a sign here, just for convention. Okay. If you keep in mind, for example, you take one element. Okay. Imagine you put shear here. The internal force here will be the opposite. On the other node, it will be the opposite, and the reaction will be the opposite. Okay. So depending on which side you are doing the cut, either up or down, you will see opposite forces. So that's why it is important to choose +1 if the elements are on the same direction of the axial vector, -1 if they are on the opposite direction.
For me, it's clear, and I don't have questions anymore, but if you want, we can, I don't know, comment script more.
Probably we can go a little bit. So this one is the preset of the script. So you only have to prepare what are the selection cuts that you want to process. Then the output will be in a text file, so you need to specify the name. And then you have cut directions, cut sides, and then I create some utility functions. I need a dot product. Okay, so dot product is a simple inner product of two vectors. Then in this case, I know that I need to perform section cuts only on 4 node elements. Okay, so here I created a simple function, actually a simple function, a map. Okay, this one in Tcl is a dictionary, and then I process every element in the finite element mesh, and for each element I get the element nodes. If the length of this vector is 4, so if it is a 4-noded element, I put it in this map. Okay, so the key of the map will be the element ID, and the value of the map is the connectivity of the element. This is just for making the algorithm faster later on. Then what we need to do is to compute the center for each selection, for each cut, because we need to perform an integration with respect to the center, okay, which will be basically the axis of the beam. Now, I decided that the axis of the beam is in the middle of your column, okay? But imagine your column is not, it was not like a rectangle or a square, but imagine it was a T-section. Probably the centroid was not in the middle, so you needed to, not to compute exactly the center, but the position of the centroid, okay? Now, in this case, the centroid is equal to the center. So I simply perform the loop. For each selection set, I get all the nodes on that selection set, and I perform the average, okay? And so you have the center there. What else? Here, make a list of all cut elements. This is for each cut, we need a list of elements information. Okay, here was just processing. Oh yeah, here was deciding, as I said before, for each cut. So for me, a cut is a list of nodes, okay? But what I need is a list of elements for each cut, okay? And as I said before, given a list of nodes, I can find all the elements attached to those nodes, okay? So the problem is this one now. let's say I'm processing this cut here that contains 3 nodes. And imagine this one is in the middle of a mesh. Now, this algorithm is basically doing a loop through all the elements in the mesh and is trying to keep only the elements that share at least 2 nodes with the selection with the cut. Okay, why? Because probably I have other elements here that share only 1 node and I don't need it. But every element which is sharing at least 2 nodes with the section cut, I need to keep them. The problem is that if I do only this, I will keep elements on both sides. And if I do the integration for equilibrium, the forces in the middle will be 0 because the 2 elements are in equilibrium, okay? That's why I need to choose only the elements on the positive direction of the selection cut. So I keep only them, okay? And I discard them. And then there was the problem. What happens if I am only on one side? So I don't have elements on this side. Well, I choose the others, but I change the sign, okay? So this is the topic of choosing the sign +1 or -1. So basically what I'm doing in this loop is finding all the elements that are connected to that selection cut, okay? It's a little bit long, the script, but basically it's doing only that. It's just a geometric tool for checking what are the nodes, what are the elements connected to the selection cut. Now you can go on. Once I've done this, for each cut, I have all the elements associated for that cut. And then I needed to prepare some stuff for the file, okay? So before writing the data in each analysis, I needed to create one text file for each cut, okay? So first of all, I prepared the formats for the file. If you know in Tcl, there is if you want to write numbers and text in a very nice formatted way, you need to use the format function in Tcl. The format function needs a string to understand how to place the values. Okay, now we are in 2 dimensions, so the only variables that we have are axial force, 1 shear, and 1 moment. And we also have the time of the analysis. Okay, so we have 4 components. So my text file will have 4 columns. So I create 2 formats, one for strings and one for doubles, which are floating point numbers, real numbers. And this one is just a format specifier. You can find what it means on the website, but basically this one is a symbol. So the percentage is a symbol for saying that that one is a placeholder. The first number here is the width of the single field of the cell. Then 0.2 means that I need 2 digit numbers, so 2 decimal numbers. And then F is the format that I want. Okay, in this case, I wanted a fixed format. So every number should have whatever it has in the front, point, 2 decimal numbers, and the F means this is a fixed format. So this one is just for writing things into a file. And then I open the files, okay? So for each cut, I get the cut name. I define a cut file name here, which is basically the cut file name format plus the cut name. So as you can see, every file will be the format that you defined at the beginning, underscore the cut name at the end, okay? Then I open the cut file. I just write the first string, which is the header, okay? So normal force, actually time and VM. So this one will be the first line in your text file. And then when you open a text file in Tcl, what you have here is a handle to a file, okay? And a handle to a file is basically an ID, an identifier for the file, so that you can reference the file later on in the analysis, okay? But I need to store them, okay? So I store them in a list of files, okay? So cut files will contain the pointer to each one of these files that now are open, okay? Then once I've done this, you can go on a little bit. Here you have the cut recorder, which is a custom procedure, okay? This custom procedure is now just defined, is not called, but it will be called later on. So you can define a procedure. Inside this procedure, what I do is simply doing a loop inside all the cut files. Then I get the current cut file. I get the data for my cut direction, all the elements, and then I perform a loop through all the elements, which is down here. You can scroll down a little bit. You can see here at line 192, I do a loop inside all the elements for this cut. I get the element forces by calling the LA response OpenSees function. This one means I want the response of the element with the LA tag, and as output, I want the force. Okay, this one basically are the forces at the ends of the element. Okay, when I do this one, I simply project these forces into the direction of my local axis because I need to transform them. So if you want to know, for example, this one is a two-dimensional vector, IF, okay, which is the fx and fy at a node. They are located in the global direction. So I need to project them in the local direction of my section cut. And you simply do this by performing this set of dot products. Okay, so if you want to understand what is the operation here, is this one. So imagine for a single node, which is here, for example, with the L response, you obtain fx and fy, which are aligned with the global axis, x and y. I put them into a vector called if. So I have a vector here called if, okay, which contain basically fx and fy. It is a two-dimensional vector, okay? And then I need to compute a local vector, en, ev, okay? So en, in, and iv are basically this vector here oriented in the local direction of the cut, which was, for example, in this case, dx and dz, okay? So basically this one is just a matter of rotation. So you can create a rotation matrix that contains in the first row, the dx axis, in the second row, the dy axis, and you do the matrix multiplication with the if vector, which is fx and fy. So what basically in is equal to this vector times this vector. So this one is a dot product, which is this one, if cut dx. And then iv is the dot product between dy and fx. Yeah? Is there a question? Okay, no, I thought someone was asking a question. So is this clear? This is basically just a rotation of a vector. Okay. Okay, so what I'm doing here, taking the global forces, I project them, I orient them in the local direction of the section cut, and then I perform an integration. Okay, n is equal to the previous n plus the n contribution coming from this node. V is equal to the previous V plus the V coming from this node. And then for the bending moments, it is equal to the previous bending moments minus, and the minus is just a matter of sign, minus the axial force for that node times the distance from the center. Okay, so if I do another drawing here, I try to draw it in 2D because it's easier to visualize it. These are my elements. This is my selection cut. I have dx here, which is the direction for the axial forces, and dz here. And I'm doing the integration with respect to the center, which is here. Okay. So, for example, if I have a lot of nodes here, like here, this one in the middle, and the one here. Each one of them produce a contribution, like en here. So you sum all the in and you obtain the total n. You sum all the iv and you obtain the total v. But then there is an extra component because the n times the distance from the center can produce a bending moment about the z-axis, okay, which is this one. So sorry, the y-axis in the local direction of the beam. The minus, because if I have a n here, okay, sorry, a positive n, which is pointing aligned with the dx in a positive distance, which is this one, along the dz, it will produce a negative bending moment because the bending moment will point in the opposite direction of minus c. That's why I need to put minus here instead of plus. So is it clear? Okay.
Yes, I think yes.
Okay, so there is a minus here just for this reason. So you always, if you want to understand if you have to put a minus or a plus, you put the vector in the direction of the positive axial direction. Then you place it in the positive distance, and you say, okay, let me do the product between a positive force and a positive distance. If it gives a positive moment, there will be a plus here. If it gives a negative moment, you have to change the sign. Okay. So when I've done all this integration, I write these three integrated values into a line of this file. Now this function will be called at every time step. Okay, so for every time step, I will open a file for that selection cut and write an extra line. Okay. Now you may say, okay, but I defined this procedure. How does STKO call this procedure? Well, once you have this procedure, you can append this procedure to a list of procedure that STKO has already initialized behind the scenes, which is called all custom functions. So whenever you want to do a custom operation in the middle of an analysis, you can write that TCOL file, a custom procedure, and you can append it to the default list of custom functions. Now, by default, this one is empty, but when you start adding functions, your functions will be called during the analysis, okay? At every step. So now you can close this one. Now, basically, we are done because now, when you run the analysis, at the end of each analysis step, STKO will call that function. Now, there is only one extra thing you need to do, which is the finalize section cuts. Because if you remember, we have opened the file. All the files are open now. We wrote into the file, but we need to close each and every file. Otherwise, if you exit from OpenSees without closing the file, there might be some problem reading the files, okay? Now, typically, the operating system should close them. But if you have a crash or something else, it may happen that the file of the content of the file are not written inside the physical file. So you always need to close the files at the end, okay? So the finalize is just a loop through all the cuts files and close the cut file handle. Okay. Once you've done this, you run the analysis, you can visualize, show them what is the output. Okay.
So we have TXT file for each section. We can open it and we have our normal shear force and moment.
So as you can see, you have the first line, which is the header that I wrote at the beginning. And then each line of this one, each line for this file is written into at the end of each and every step of the analysis. Now you can show them, if you have the results, you can show some results to them just to show how they relate with theoretical solutions. Anyway,
yes, for example,
was it useful for your analysis?
Yes, it's very, very useful for my analysis. I'm still proceeding with different specimens, but I think it works perfectly. I'm very, very happy about it. Thank you a lot.
Maybe can you show just a couple of images of your model, like the results? I mean, the damage or the damage of the infields. I think I like
I have them so many.
Yeah, just a few of them. So I think they are very interesting with the reason.
This is with the big bricks we had, for example. Yeah, we had different specimens. We have also crash of the bricks. So it's quite coincide also. Pushover curves, it's quite good, and it's just not open. We also have Mirhabi Shing, where we have very, very small bricks, and it also working there.
That's because people normally think about OpenSees just as a frame element program, but it's way more than this. So that's the reason because I ask you. Thank you.
Thank you.
Anyway, the results are really good. So your models are really fine. Very nice.
Thank you. I hope to graduate in 3 weeks.
And then we have to adopt you. So there's a problem.
Yeah. Thank you. Okay, I can stop to share.
Yeah, if any other questions about this topic, otherwise we can pass to other questions. Is it clear to everyone what we have done for Valentina? If you want, you can switch on your microphone, your camera. You can share your thoughts about this one. Or if you have any other questions, whatever you want.
Thank you very much for that presentation, and the explanation was good. I think was very specific for that case. It was a confined wall, and you modeled masonry with 2D elements as well as the concrete elements, if I understood.
Actually, this was an infill wall, so it wasn't exactly a confined masonry, but it's an infill frame with infills.
Okay, so I'm also working on, I'm working on confined buildings, and I have a question that I uploaded some months ago to the forum, but I couldn't solve my difficulty, which was related with giving a contact elements between masonry and beam elements. So maybe I can share so you can see.
Yeah, sure.
So this is the building. This is a typical dwelling from Cuenca in Ecuador, and I modeled the building and tried to use contact elements between the confining columns, reinforced columns, and the walls, which were modeled with shell elements, with fiber shell elements. But when I used contact elements, I couldn't reach convergence. The analysis stopped very soon. So I changed my model by using, by assigning constraints equal Dove constraints, and then the problem was solved. But actually, I couldn't extract all information. I can only find from this analysis well, the contribution of the columns in the shear, but not actually I cannot actually find the interaction between the two elements. So I think maybe the reason of why I was not reaching convergence was due to the local axis or the definition of my constraints. Or
probably. Let me see. First of all, what kind of contact element are you using?
Well, here I am not using it contact element anymore. I just used the equal Dove because it was not working.
Okay, so with the equal Dove, what you've done is basically assuming that the beam and the shell, they don't have any gap. Okay.
Exactly.
But when you were trying to use the contact element, what kind of element were you using?
I was using, if I can check it here first, I used the one, let me define it here, not here, but here. I think it was a zero length element. Yeah.
This one are uniaxial materials. No, probably you created a zero length element.
Yes.
Then it's not here, it's not in physical property, it is in element properties.
I had this, yeah, this one. And I use one that was just presented in a previous seminar. I think is
So the ASD, yeah, zero length.
Yeah, this one.
Okay. So now it really depends on, yeah, as far as I can see how you model it, you didn't create any gap between the beam and the shell. Okay, so
No.
you need to pay attention to what kind of values you are using, but yeah, the easiest thing for you now to understand how it works is not to do it in such a large model. Okay, probably it's easier if you do it on a two-dimensional small model. You try to understand if you are getting correct with the local axis, because the problem with these zero length elements is that the local axis should always point in the same direction of master node. Okay, so imagine you have, so this one is the main problem of contact elements in OpenSees now, is that imagine you have two nodes, okay, and they are overlapped, okay, so they are in the same position. I'm drawing them slightly separated just for convenience. But when you define an interaction and you choose the first surface as a master and the second surface as a slave, what I will do, what STKO will do, is to create a link between the master node, which is the first node, the first node N1, and the second node, which is N2. Okay, and then the gap will be computed as, so like the U will be computed as U2 minus U1. Okay, and then this value will be projected onto the local axis. So if my local axis points in the same direction, okay, so this one will keep the same sign. So if N2 moves forward, this one will be a gap, so will not have any contact force. If it will move inward like this in the opposite direction of my axis, it will be contact. But if for some reason you do a mistake and you assign a local axis which is in the opposite direction, you will not have any, or you will have the opposite of the contact. Okay, so it will be in contact when they will detach, and the opposite. So the first thing that you need to check is the local axis. I say this also because you have another problem here. When you do not draw, like Valentina was drawing the beam with a solid element. So in that case, it was pretty easy because you have your column here made of several finite elements. Then you have your shell here and you have contact here in between. And then you have the shell here and other contact on the other side. Now, in your case, it's a little bit different because you have just one beam. Then you have a shell on one side and a shell on the other side. Okay, so this one is a shell, this one is another shell, and here you have a beam. So with this beam, you have to create a contact, an interaction that goes in this direction, so master and slave, and then you do the same with another interaction, master towards slave. Now, at these two interactions, you need to assign two different local axes. On this side, the local axis should point in this direction, and in this side, the local axis should point in this direction. For contact, the normal axis in 2D is the dy direction. In 3 dimension, it is the dz direction, or let me check if it was the dz or dx. I will do a quick check in just a second. Let me go on my computer. I think it was dx, but I need to check it. Just give me a second. So STKO, external solvers, OpenSees, element properties, zero length element is the implex. Then I get the local axis. Where is it? Direction. If the value is measured in 2, we have this one. Okay, rigid gap, orientation type. From link direction, from elements, or from local axis, I get, yeah. If well, I will share my screen so you can see it here because there is no documentation for that. But I share just a second my screen, and then you can share. Yeah.
I have to stop sharing?
No, it will stop automatically. So this one is the Python file for the zero length contact ASD implex. Now you have three options for local axis: the from element option, from link direction, or the default one is from local axis, the one that you have. If I am in 2D, I took the column number 1. Keep in mind that it starts from 0, 1, 2. So column number 1 is the second column in 2D, which is the y-axis. In 3D is the z-axis. Okay. So in your case, you are in 3D. It means that I need to do a drawing. Okay, so you are in 3D. This one is your beam. This one is your shell. Imagine that the beam is the master. The shell is the slave. Your link will point from master to slave. You need to create a local axis whose z direction is this one. The x and y can be whatever you want. One will be the axis of the beam, and the other will be normal to these two axes. Okay. But the z-axis should point from the master to the slave. And since you have a two-sided contact, so the shell is on both directions, here you need to create another interaction that goes from the master to the slave with another local axis, which is this one. Now, this is very difficult. That's why we implemented a tool, which is this one. But now probably it's difficult for you. Because if you
yes, it takes a lot of time.
Yeah, it takes a lot of time because you have to create a lot of interaction. That's why if you create the shell is slightly separated from the beam. Okay, you create a small gap between the shell and the beam. You can use the from link direction. So the nice thing is that when you create a small gap between the shell and the beam, I can compute a direction that goes from the master to the slave without the need for you to assign a local axis. The problem is that when the master and the slave are coinciding, I cannot compute the direction between them because it is a zero vector. Okay, so if you create a small gap, and I explain it in the webinar about contact element, okay, you create a small gap, and then I will be able to compute the distance from the slave to the master. And so we'll be able to compute automatically the contact direction. And then optionally, you can say that this initial gap is rigid. Okay, so it's not a real initial gap. So if you look into the webinar, try to look at the options from link direction and initial gap. Those are the two options that you need. The only problem for you is that you need to refine your model a little bit because you need to create a little gap between the shell and the beam. Okay, it will be much easier than creating a lot of different local axes, for sure.
Yes, yes, I will try. I did try in a simple wall, and it was working, but I didn't have clear, perhaps the creation of new local axis. Then when I implemented in the whole model, then I start having problems, and then I think it will be a good idea to change the model as you advise now with the small gap. It doesn't matter how much small is the gap.
No, it doesn't matter. Actually, if you want to create a realistic simulation, the gap should be half of the depth of your section. Okay, so imagine, let me share once again the screen. So in reality, you have a beam. This one is the width of the beam, and then you have the shell wall here. Okay, so this one is your wall on the other direction, and here you have a column. Okay, now instead of drawing the column in 2 or 3 dimensions as Valentina did, you do it with a column element which has zero thickness.
So it's half the width.
Yeah, half and half. What I do if you select from link direction and rigid gap is that I don't do a contact directly between this node and this node. I create a temporary node here, which is actually at the same location of the slave. I create a rigid link here, and then here I create a contact element. But the advantage is that since I have this distance, I'm able to compute the contact direction automatically.
Okay, and what element should I use for proceeding in this way?
It's the same. When you select zero length ASD implex, you go on the orientation type. Let me see if I can show it to you right now. I need to share my screen. Okay, if I'm here, I go on element properties, zero length elements, ASD implex. You know, by default, the orientation type is from local axis. It means I will take the contact direction from the local axis you provide. Otherwise, you can choose from element. I explained this one in the webinar, but this is fine when you do surface to surface contact. Otherwise, if you do beam to surface or beam to solid contact, you can use from link direction. And here there is a description. If you choose from link direction, okay, and then you click on rigid gap, what I do is that first I check that your slave and master are not overlapping. If they are not overlapping, I can compute the distance between them and the vector pointing from the master to the slave, okay? And then if you click on rigid gap, I will consider that gap as rigid, okay? As if it was filled with other material. This one is perfectly fine in your case, okay? So this one is the typical setting that I use if I have to create contact of a pile in a soil, okay? So I create a hole which has the radius of the pile. The pile is modeled as a beam, and then I create this sort of contacts between the beam elements, the beam nodes, and the nodes on the soil domain. For you, it's the same, but it will be from the beam to the shell. It will be much easier because the direction is taken automatically from the geometry, not from the local axis you provide. So it will be much faster for you. And it will also be slightly more correct because it takes into account the thickness of the beam. Okay?
Okay, that was very helpful. Thank you.
You can try, but you said that you posted it on the forum and we didn't answer.
No, you did answer, but well, it was not, it didn't solve the problem.
Okay.
So yeah, it was not answered like you explain it right now. So
okay, so probably I misunderstood the question. Yeah, you can try to use this methodology, and then you can get back on the forum and let's see if it is solved.
Yeah, sure, I will implement it.
Contact is always a problem.
Yeah.
So when you do the ASD implex, you have to, when you use contact in general, you have to pay attention to the contact direction, and you need to pay attention to the contact penalty stiffnesses. Because if you choose numbers which are too low or too high, your system can be ill-conditioned. So you may have convergence problem, not because there is a nonlinearity, but because the numbers in your system matrix are very unbalanced. Imagine that you choose a value for contact stiffness, which is 10 or 20 order of times, the 20 order of magnitudes larger than the larger stiffness in your matrix, okay? All the other numbers will be seen at 0. So you need to pay attention to the penalty values that you have. So just to have an idea, you can take, for example, what is the axial stiffness of your beam? So you do EA over L. This is a typical stiffness of your model. Take that one, which is, for example, 1000, and then you say, okay, it would be 1 to the power of 3. My contact stiffness can be 3 order of magnitudes more than that. But do not make it too much larger, otherwise your matrix will be singular. And then, if all the settings are fine, you can still have problems because contact is a very hard condition. So it can be either non-linear or linear, like you have a very high stiffness sometimes when you have contact and a 0 stiffness when you don't have any contact. So it can always be a problem. That's why we implemented the implex algorithm. With the implex algorithm, convergence will be much easier to achieve. Okay, so you can also use the implex algorithm for that. Okay, so try all these things, but yeah, keep in mind that contact analysis is not so easy. It's always a mess.
Yeah. Thank you very much.
You're welcome. Is there any other question, some curiosities? If you had some problems?
Hi.
Hi, Carlotta.
Carlotta. Good evening. I'm a really beginner in using STKO. And so I have a basic question. How can I apply the solid self-weight in a 2D vertical analysis? I have to use phase force, or I can set the specific weight in add soil physical properties?
Okay, actually, it is the same in terms of the total force that you apply. Okay. First of all, you have to pay attention. You're using standard solid elements for soils or UP elements, because there is a difference. You can use standard displacement based elements. Standard, okay. Because in standard element, there is an option. Oh, let me share my screen so you can see it. Because sometimes people have done this mistake. So if you use standard elements either in 2D or 3D, for example, let's go into the analysis. Quadrilateral elements, quad. Okay, if you want to assign the self-weight here, you can click on optional, and then you have B1, B2. As you can see here, this one is the constant body force. So is clearly explained as a body force. So in your case, it will be rho times G. Okay. Okay, so in your case, for example, you can put minus whatever it is here. Okay. Now this one is a self-weight, so force per unit volume. You can either do it like this, or you can create a condition and what is it? Load, force. If you are in 2D, a phase force, or if you are in 3D, a volume force. Now, if you are in 3D and you click on volume force, you enter exactly the same value. So a force per unit volume. If you're in 2D, so if you go on load, force, phase force, here you have to put the same value you put into the element times the thickness, okay? Because a phase force is actually a force on a plane, okay? So it's a force per unit area, which is in your case, it will be the self-weight times the thickness of your model, okay? Now, in terms of results, they will be the same. So the total force will always be the self-weight times the total volume of your body. So if you do the, if you sum all the reaction, that will be the output.
Okay.
The difference is the way in which OpenSees applies this force. If you use the option from the element, the force will be applied all in one step. Okay, so it doesn't matter if your analysis is done in 10 steps or 100, or I can do actually a test for you so you can see what's the difference. So let's create a simple model. Let me save it here. Self-weight. Okay. We are in 2D now. I will create some random element. I don't care about the properties. Okay, so this one is an element. Let's create a physical property just for simplicity. An ND material, other ND material, elastic isotropic, and let's put 1000 here, 0.2, and let's put 100. Okay. Okay, so let's put a row. Actually, a row. I'm not interested in row here. I'm not doing the dynamics. I just want to assign this one. Then element property with self-weight, and then I will create another one without self-weight. Okay, so you can see the comparison. Where is it? Quad. Let's give it a thickness of 10. Okay, plane strain or plane stress is not important in this case. And then here I put minus 10, okay, in B2. Now keep in mind, this one will be force per unit volume, okay? Now this one will be multiplied by the total, inside OpenSees, this one will be multiplied by the total surface of the quad elements times the thickness, which in this case is 10, okay?
Mm-hmm.
And then assign it to this one. Let me create a simple condition, like constraint, single point, fix. Let me fix everything at the base. Okay, so the self weight is already assigned. Let's create a recorder. Result, displacement and reaction forces, because I want to see the reactions. And then patterns, add pattern, constraint pattern. Then I add boundary condition for the fixity. I don't need to add any load because I don't have any load here. The load is applied directly inside the element. So I just create an analysis. Let's do a static analysis now. And then you will see what kind of problems you may have with dynamic analysis. Static plane is fine. Everything is fine here. We are doing a linear analysis, so there is no problem. Here, factor ones. Load control 1. And we can do it in, let's do it in 10 time steps, okay? So you may imagine that your brick will slightly go down, okay, step by step. Okay, let's see what happens. Now let's create a mesh here, faces, quad structure, assign, done. And let's do a simple mesh with only one element. Faces, select, structure, quad, assign, done, in mesh. Okay, we have just one element here. Save it and let's run it. Okay. So let's open the results. Which is in DB shear, self weight. Okay. So let's see what is the total reaction. Structure data on nodes. Stage 1. Time step is fine. Reaction force in Y direction. And then I select the two bottom nodes. Next. And add. So we do a sum. And this one is the total Fy reaction. So the value is 1 to the power of 6. Yes. And let's say if it is correct, because it was, we put minus 10 times the thickness, which was 10 times 100 times 100. Okay, because this one is the length of my, let me make sure it is like that. Query geometry, query length 100. Okay, so that's fine. So it's 1 to the power of 6. Now let's see what happens. So the total reaction is fine, but if I do an animation, you will see that it doesn't change. Okay, so everything has been applied in a single step. So what's the problem? In terms of output is not a problem. When you have a linear analysis is not a problem, but when you have a nonlinear analysis or a dynamic analysis, applying the load in a single step can be a problem. Because imagine this load is very high and you have no linearities, you will not be able to solve it. So you will try to reduce your time step, but it won't work, because even if you reduce the time step, the entire load will be applied in a single step. Okay, so you will not be able to solve the non-convergence. Instead, if you do dynamic analysis, either linear or non-linear, if you apply the entire load in a short time, okay, it will start bouncing. Okay, so you will need to apply the load in a distributed fashion. Okay, so to do this, what you need to do is not to follow this approach. Now let me copy this output here just to make sure that we obtain the same results but with a different element. So let me clone this element, edit, and I don't want to use any self-weight on the second geometry, okay? So the second geometry doesn't have any self-weight. Now, of course, if I do, or let me see, the fixity condition should be also here, otherwise it will be singular. Okay, mesh, build mesh. If I do the analysis now, I will see that one moves and the other doesn't, of course. Reload. Okay, so this one is not moving because there is no load applied on it. Now I want to apply a load which is equivalent to the self-weight applied here. So I go on condition, I go on load, force. This is a surface, so I need a phase force. Phase force. Now what is the value here? A phase force is actually a force per unit area. So it was minus 10 times the thickness, which is 10 once again. So minus 100, okay? Which will be basically the self-weight times the thickness of my model. I select this phase and press OK. Now, of course, as you can see, this force has been defined, but it is not used in the analysis. In fact, it is black, it's not blue. So I need to create a time series, a load pattern. But before the load pattern, I need a time series. I want this load to be applied incrementally, so I need a linear time series. So I go on the time series and I choose linear. In this way, basically, my load will be applied step by step, and it will reach 100% at time 1. Okay, this is fine for me. Let me move this one. Okay, and then I can create the load pattern. Add pattern, load pattern, time series, the linear time series, and then this phase force goes into the load vector. Okay, and now you can see that it becomes blue. Of course, now I need to pull it up before the analysis. I can save it and run it. Let's go back to the results. Reload. Reload. Okay, something here. Yeah, let me see why. Phase force condition is applied here. Oh, yeah, my bad, my mistake. Look here, where did they put it? In the Z direction. But when I am in 2D, actually should be in the Y direction, okay? Because I have only 2 dimensions. Okay, run the analysis again. And reload. Okay, now the output is the same, but if I do an animation, okay, I will see that the second one is arriving at 100% of the load step by step. Okay, so this one is the main difference. As you can see, the output is the same because when you define the phase force or any distributed force in a continuum domain, STKO performs a nodal lumping in the same way it is computed inside OpenSees. So the output will be the same. The only difference is that the load is applied incrementally. That's all.
Okay. Thank you.
Okay.
Yes, yes. Thank you.
And that's why I was asking you if you use standard elements or UP elements, because if you start using UP elements, which are elements for displacement and water for pressure, they have a different definition. When you assign the self-weight, you don't have to assign the self-weight, but only the gravity acceleration. Because internally, that element takes the acceleration vector you assign to the element, it multiplies this vector to the raw value of the material, and then it obtains the self-weight. But that's a problem that you will encounter if you will use UP elements.
Okay, okay. Thank you.
You're welcome. Is there any other questions?
Hi, Massimo.
Hey, how are you?
Hi. I am fine, thanks. And you?
Fine, fine.
I hope everyone is okay. I have 2 questions. First one is, what is the easiest way to model a shear wall with confined end zones with fibers?
So confined
end zones, you know, you can put stirrups like columns in regular shear walls.
Yeah, the problem is that stirrups, I mean, that's a problem in the shear wall. I mean, if you have stirrups in a shell, keep in mind that everything that happens through the thickness of the shell. So can you do a sketch to explain how it is placed inside the shell?
Yeah.
Even sharing your screen.
Yeah. Actually, I'm on my tablet.
Yeah.
And I'm sketching it now. Going as fast. This is the wall that I want to
okay, no, that is a problem. That's why if you do it with solid elements, okay, and you use a three-dimensional material model like DamagedPC 3D, you can just put a stirrup inside the solid, okay, because the three-dimensional element will see the confining effect of the stirrup, okay, because a three-dimensional element has a three-dimensional state of stress. When you do a shell, or the same when you do a fiber cross-section of a beam, you are missing the out-of-plane stress. Like in a beam, you have only a uniaxial stress. In a shell, you have a plane state of stress plus the out-of-plane shear, but you don't have the out-of-plane stress. So basically, you are not able to see the effect of the stirrups compressing the concrete or the masonry, whatever it is, in the out-of-plane direction. So you will never be able to automatically compute the confinement with the three-dimensional material like DamagedPC 3D. So the only option that you have there is to, let me do a drawing.
Actually, Massimo, I want to calculate confined concrete stress by myself.
Okay, so if you, for example, if you can expect what is the vertical weight, and then you can do a computation of the confinement, what you can do is to take your shell, okay, for your wall. You know that the confining part is only a small portion here and here. You simply assign two different sections. So the section here will be made of a, let me do a layer cross section here. Okay, so let's say you divide it in many fibers through the section, like the top fiber, the bottom fiber, and some fibers in the middle. Okay, now all the fibers in the middle part will be made of the same material. Let's call it concrete 0, which is the unconfined concrete. Yeah. And in these two sections, you have the unconfined in the core, so C0, C0, and in the 3 in the middle, you have CC, which is the confined version pre-computed by you. Okay.
Okay.
Which is basically the same thing that you would do with a beam element, because otherwise there is no way to account automatically for confinement like you could do in 3 dimensions.
Okay, I have to model the end-zone separately. Yeah.
Yeah.
Okay. And the second question is, you know, SSI analysis takes too much time, and I want to pause the analysis in a desktop computer in a safe way. Is it possible?
I mean, it is taking too much, so you want to stop OpenSees.
Pause the OpenSees and shut down the computer and continue later.
No, unfortunately, that's not possible. I mean, yeah. In theory, it is possible. It's called the restart command. There is a restart command in OpenSees that basically, actually, it's called the database command, which basically allows you to tell OpenSees, let's say, for example, every 10 steps, save the entire model into a database. For the entire model, I mean all the nodes, reaction, displacement, all the internal variables of the element. So it's like creating a snapshot of your model at a certain point. Of course, you will not do it every 10 step because otherwise it will take too much. So let's say every 10 or 110 steps, you do a snapshot. And if something happens, like your computer crashes or you crash OpenSees because you want to continue later, you can open OpenSees again and reload the database, okay? So this is what happens in theory with that command. The only problem is that the database command has not been updated since many, many years. So basically it will not work, okay? It will work only with some components written many years ago. So it's not an option now. You don't have this possibility. I'm sorry. Probably someone will try to implement it in the future, but it will take too much time because it has not been kept up to date from many, many years.
Okay, thank you very much.
You're very welcome. There any other question?
Hello, Dr. Massimo. My question is regarding the calibration of the materials using OpenSees. So let me share my screen. I would like to make it a bit more tangible. Okay, so I think you can see my screen, right?
Yeah, I can see it.
Yeah. So this is like an anchor bolt. We apply the shear loading, and we find the shear hysteresis of the bolt.
Yeah.
So now when I use the SAP 2000 multilinear link element using the part hysteresis, so I was somehow able to catch the effect, and it was working well. But when it comes to the OpenSees, I was a bit blind about the STKO, how I can calibrate my experimental model with this one.
Okay.
Yeah.
Yeah, so general for testing, I mean, I'm not a specialist of this kind of material, but I think there is something like this in OpenSees already. Let me share my screen.
Okay.
So whenever you want to test something in STKO, what you can do is to, well, first of all, you need to understand if there are material models in OpenSees that resemble what you want to do, okay? And then you can use the material tester. Now, in your case, your materials are under uniaxial. Then you can use the material tester on the right-hand side, like, for example, if I go on concrete material, which is a concrete here, you can set up your parameters, and then you do a test. Then I will show you how to do it. I'm not sure about what kind of material you can use there, but I think there are some materials for screws and stuff like that. Other uniaxial materials. It was probably this one. Let me see. This one kind of material that. Is this something that can resemble what you want to do?
Yeah, exactly, somehow.
Yeah, probably there are others, but this one, so material provides the implementation of one-dimensional hysteresis model. There is not much here, just to understand what it is. There are some references.
Yeah, it's for the wood structure, in my opinion. Yeah, wood frame.
Actions of wood structure. So probably it can be calibrated also for your case. So you have some sort of parameters to compute the hardening part, the softening part, and then the pinching. So probably it's similar to what you want to do. In your case, I think you don't have an initial hardening like this. You have a gap and then it goes up, right?
Exactly.
It's something like that. So probably, I don't know if it is something like this here, otherwise, but the problem is that you cannot even use the multilinear. Probably with the multilinear. So, I don't know if you can. Because the
basically they use the finching for material. I found some they use pinching for material.
Pinching 4 is fine for the pinching, but the same thing, it starts with the backbone envelope. Now, from what I've seen in your example is that you were actually, you had something like this. It starts, then it gains some stiffness, even from the very beginning. Is it right? So like
exactly.
Something that goes in contact and then it goes upward. I don't know if there is something in OpenSees. Probably you can simulate it. You a gap element because there is a gap elastoplastic element, and then you can add a little bit of strain hardening, I think. Let me see if there is a gap element here, like materials, uniaxial, or probably let me see the self-centering, for instance. Not this one. I was thinking about the gap material, but I'm not sure if it is there. Uniaxial.
Yeah.
But there should be some gap here. Elastic, perfectly plastic gap. Let me see what it looks like. Yes, you can define a gap material in one direction.
Mm-hmm.
And the problem is that you don't have the gap material in the other direction.
Mm-hmm.
Gap is only, it's not so easy. I mean,
Yeah.
the part is not so easy because for the pinching, there is no problem. The only problem is that you have an initial hardening. I don't know if it is possible with the multilinear. This is the last chance, but otherwise you can see probably there is some option here because there are many of them. The multilinear, where is the multilinear? Let's try to see what happens if you do an increasing stiffness, because actually this material is thought for strain hardening materials with stiffnesses that diminish. Okay, so the second stiffness is not higher than the first one, but let's see what happens if I say, okay, I have displacement of 1, then I have displacement of 2 and displacement of 3. Okay, that's for example 3 displacements. And then I give a force which is 1, then it increases a lot, like 10, and then it remains pretty flat. And then 10.5. Let's see what happens if I do a monotonic test. Actually, it gives an error because, yeah, the multilinear is thought for, I don't know, 4 entries, so probably I can do it. I just need to apply an extra value, like 3, 4, and we can keep it flat. 10.5. Okay, so what I can do here is to create an initial gap, and then it gains stiffness. But if I do a linear increasing, let's do 10 steps, 100, and it slowly reaches 4. Let's do a test. You see, it's not what you want because it goes back with the same stiffness. It doesn't go back with the initial one. Yeah. So this is not what you want. I mean, probably the easiest way would be to have a look at all this material. If some of them be something that I don't know what are these ones, or cast material. Probably someone here will be the kind of material that you want, but you really need to go. Oh, probably this one. Probably this one is the one that is fine for you.
Yeah, somehow.
Statistical forms, statistical panels. I don't know what is the initial part, because the initial part seems to be always a strain hardening. Well, the easiest way would be to look into all the material models in OpenSees. I think that someone will have the material that you need. For sure, someone has already implemented it. The problem is that all of them that are there with pinching, they start with a backbone. In your case, instead, you have an initial slow stiffness, then it gains the real stiffness later on.
Yeah, because anyway, there is the gap is due to the ball size and the size of the hole that we
Problem
drilled
is
for
that
the hole.
there is something for gap, as I've shown
Yeah.
before. Let me share my screen once again. But the problem is that it's only one direction. So probably what you can do is to create two springs, one working in one direction and one working in the other. This is probably one thing that you can do, because for the gap, it is fine. There is a gap material, but it works only in one direction. I've seen that there is another gap material, hyperbolic gap. I don't know how it works. Let me see if it is a, no, it is still on only one direction. Always on one direction, because what you can do actually is to create a gap material like this, material, uniaxial, some standard, perfectly plastic with gap. Let's say you have 1000 here, and you have 10, and then you have a gap of 1. If I do a cyclic test, I do 10 steps, probably more than this. Oh, the target strain should, but the gap should be more than this. That's the 0.1. Okay, so you have a gap and then it goes up. Okay, so this is fine, but you can see it doesn't happen in the other direction. Now imagine you do this one. Then you create another material, which is elastic. Let's see how it works. Some standard elastic, and let's give it a small strain hardening, like it was 1000 initial stiffness, let's say 10. And then you can place them in parallel. Let's see what happened. Material, uniaxial, some standard, parallel. And then you put 2. So you want the gap material and the strain hardening. The factors would be 1 and 1. 1 and 1. Oh, but the problem is that then you don't have a, then you have a gap. Or probably, but it's fine because it is very small. Let's see what happens. Oh, let me do, 10 steps. Yeah, the problem is that you don't gain anything here. It just goes up, but it also goes up here. It's not, I mean, probably you need to go into all the material models here and see what works better for you, because it doesn't look like there is a material already for that, but probably some of them will work. So no, probably the guy, I don't know what is the cast material. No.
Let me see.
Otherwise, if you have some experience, because you said that you simulated it with another software, or you did something.
Yeah, I use, because the main thing is like I have 2 experimental testing, one for the pipe with T joints, and I need to define the joint using OpenSees. And one reference study I found, they are using 0 length flexural hinge. So and for the pipe they're using elastic beam column, and they are getting the experimental test. But in case of the anchor bolt, I'm using many elements, but it's not giving me the results. But in SAP 2000, when I use the multilinear link element with the pivot hysteresis, it's giving me the exact value. So I was not sure whether it's be correct or not.
No, because the only problem in OpenSees, probably is correct in SAP. I don't know about SAP, but in OpenSees, when you define the multilinear, when you define the different stiffnesses for the hardening, it uses the same stiffnesses for unloading. While in your case, it's different because you have some stiffnesses for hardening, and while for unloading, the kind of stiffnesses are different. So you cannot use the multilinear, which is in OpenSees, for doing this. Okay.
All right,
probably you can use the SAW model. Probably the SAW model is what you can use, because if I remember correctly, let me check OpenSees. source. There is the source material. If you are lucky and you can specify a different thickness than K+1, but not, I don't think so. No, the other thickness is always less than the initial one. You cannot place a gap here. It's not so easy. It's not so easy. I mean, there are a lot of tools. The problem is that they are lacking the initial gap.
I see.
Yeah.
Okay. Thank you so much.
Welcome. Okay, so thank you everyone, and thank you for joining this question and answer. And let's see, probably the next webinar will not be a question and answer. It will be a standard webinar on some of the new features we will add in the next STKO version, because in 1 month from now, we're going to have version 3.0 of STKO. So there will be a lot of new features. If we can release it in time, for sure it will be a webinar on that. Otherwise, we will propose another topic. Of course, if you want to suggest some topic for next webinars, you can send us emails. Okay, so we will be more than happy to try to prepare a webinar according to your requests. Okay. So good evening to everyone, and thank you for joining this webinar.
Thank you.
Bye.
Thank you. Bye bye.
Thank you very much. Thank you.